So here we're going to talk about the RLC series circuit that's shown right here. We know that the potential gain across this AC component is equal to delta V max sine omega t, and the current is the same at any point throughout the circuit, and it's going to be equal to I max sine omega t minus phi. Phi is some phase angle. We're going to figure out what that is in a bit. So this gain in potential is equal to the sum of the drop in potentials, where we have delta VR, the drop across the resistor, is I max R sine omega t. Across the inductor, I max XL sine omega t plus pi over 2. Across the capacitor, I max XC sine omega t minus pi over 2. We already saw all of this stuff in the last video. What's in pink, we're going to call the maximum values of these potential differences, or the potential drops across these components. So this is capital delta VR, delta VL, and delta VC. What we want to do is then add up all of these components. So here, if we look at their phasors, to add them up, the first thing to do is subtract XC from XL. So we have something that looks like this. This is delta VL minus delta VC. And then here we have delta VR. We want to figure out what this component is here when we add them up. So all we have to do is square them and then take the square root of the square, shown here. So then delta V max is equal to square root of delta VR squared plus delta VL minus delta VC squared. Take what these values are in pink, plug them in, simplify it a bit, and you get delta V max is equal to I max square root of R squared plus XL minus XC squared. This is called the impedance, and is essentially just a combination of all of the resistance components inside of your circuit. We can then say that delta V max is equal to I max times Z. To find out what phi is, the phase angle is just the angle between I max and delta V max. We just got to use our trigonometry again. It's the inverse tan of delta VL minus delta VC divided by delta VR. Simplify that down and we get XL minus XC divided by R. So then, if we want to talk about what is the power delivered to an RLC circuit, we know that P average is equal to I RMS delta V RMS cosine of phi, and it's also equal to I squared RMS times R. If we want to use what we found, so we found out what Z is, we know what I max is, what we have to do is plug these values in. So I RMS is going to be I RMS is going to be equal to delta V RMS divided by Z, and that comes from this expression right here. So all we do is square them and then multiply that by R to get this, and then plug in what Z is into this equation. The last thing we want to look at is resonance. Hopefully you've heard about this before from classical mechanics. It's essentially when the circuit exhibits a maximum response, and this is going to happen when I RMS is maximized. So again, I RMS is delta V RMS divided by Z. We know what Z is, we just plug it in here. This becomes maximized when XL minus XC is equal to 0. When this happens, it's going to be at a frequency called the resonance frequencies, because remember, XL is just omega times L. XC is 1 over omega naught, 1 over omega C. We use the naught notation here to just denote that at this specific frequency, omega naught, we have the maximum response, so we call this the resonance frequency, being 1 over square root of L times C. What we're going to do now is take this here, right, this P average equation that we found, and then plug in all of our values. So what I mean by that is plug in our XL values and our XC, and then simplify it down until it looks like something like this. So essentially, this omega naught was just a 1 over square root of L over C, right? So in the equation, this was there, so then we can just replace it by omega naught. And then what we see is that when omega, our frequency, is equal to our resonant frequency, we have a maximum power being delivered to our circuit with a value of delta V RMS squared over R. The last thing we can look at is something called the quality factor. It's essentially a value that denotes how efficiently the energy is transferred to our RLC circuit. All it is, it's a number. It's equal to omega naught, our resonance frequency, divided by delta omega. delta omega is equal to R divided by L. It's something that you can find graphically as well. So if you plot I versus omega, you're going to get this peak. It's not going to be a very perfect peak in real life. And the delta omega is the full width at half maximum. So you figure out, okay, like what is my half maximum of my peak? And then you got to figure out how wide is my peak at that point here. So that's what you plug in right there. And then you get a value for Q. The higher the Q, the more efficiently the energy is transferred. That is about it. In the next videos, we're going to be going over some problems that deal with all of this.